A random process that we come across routinely in our daily lives, perhaps without being aware of it, is communications, binary data flow. A binary data flow can be considered as essentially consisting of randomly occurring zeros and ones. This is actually quite similar to what we have been considering for the random variables and probability case. A very simple example, which is basically a coin toss. Coin toss also indeed consists of two cases. Just like the 0 and 1 bits, we have tails and heads, and they come with equal probability. Each individual coin flip can be considered as an observation of an experiment. Just like in a communication receiver, each time we sample the data flow, we receive either a 0 and 1, and we can model them as the observation of an experiment. We model the observation as a random variable. At any given time t, the observation is either a 0 or a 1 with equal probability, which is 0.5. If we continue the experiment and collect observations labeled with a timestamp t, we obtain a time function. But can this be really considered a random process? There is more to a random process than just a time function. Let's take a look at another example to get a better perspective. Consider another example concerning the measurement of a sine wave from a reference oscillator. We have a sine wave where the amplitude, frequency and phase of the sine wave are unknown but modeled by a probability distribution. An experiment consists of choosing an oscillator and measuring it, where each measurement is an observation. And as you see, we can observe either one of these perfect sinusoids. So, just to keep the example simple, we assume the oscillators are stable and they suffer no amplitude or phase drift. So, no randomness in the sine wave except the controlling parameters, which are the initial phase, the frequency, the amplitude. But then where is the randomness again? What do we observe here? Considering the time function as in the first example, after the first measurement there appears to be no randomness. In this setting we know what the amplitude, frequency and phase will be at a time instant if we measure these parameters at an earlier time instant. But consider here the whole process. The first action we took was the selection of an oscillator. Here we have the randomness, and whatever randomness we have at that initial moment is actually still there throughout all observations. Now consider multiple experiments. That is, we choose a new oscillator each time and start taking measurements, and we repeat this experiment multiple times. Each time we choose a random oscillator and start our measurements as t0. At a later time t, over all experiments, we measure parameters that can be modeled by a probability distribution. We have, for example, a uniform distribution for the initial phase, and we can have perhaps Gaussian distributions for the amplitude and frequency. We have a random process here. If we fix the time over all experiments, the parameters we measure are random variables with a distribution function. After all these examples, we can formally define a random process. We consider an experiment which started with choosing an oscillator in the previous examples. Each choice we make yields outcomes, which form the space S that consists of all possible outcomes. For each outcome, there is a time function that represents time-stamped observations. This time function, as we saw in the examples, can be understood better by considering four cases. First, when both are variables, we have a family of time functions, and that is the random process in its widest definition. However, we can fix the controlling parameters. So assume we are just considering the phase where we already made the choice, and it's just the time-dependent observations. So that is a single time function. And as you saw in the previous examples, after the first choice is made, the time functions may be completely deterministic. But then there's still the randomness. Consider what happens when we fix the time. There's the third interpretation, third way to think about this. If we have a random process and if we fix the time, over all ensembles, over all possible choices we can make, we still obtain a random variable. So time is fixed, the controlling parameter is variable, we still obtain a random variable. Finally, of course, we can fix both the time and the controlling variables. In that case, we will just obtain a single number. We can now consider what can we analyze about these processes. What are the statistics that we can use to investigate the properties of random processes? When defining the statistics of a random process, the key is the random process becoming a random variable when the time is fixed. Once we fix the time and investigate the properties of a random process over all ensembles, we can utilize the same tools we developed for describing the properties of random variables. For a random variable, we use the probability distribution function and probability density function, which are defined in this slide. For a random process, we use the same probability distribution function definition by focusing on the time variable. Our definition of the probability distribution function is valid for any time instance. This means we end up with a function that is defined with respect to time. In other words, the probability distribution function is time dependent. The interpretation of the distribution function is as follows. For all time functions x corresponding to all realizations of the controlling parameters, the probability that the function x does not exceed a certain value at the specified time t gives the distribution function. Now let's see an example. Consider again the random sine signals example. The controlling parameters for the sine waves, which are the amplitude, the frequency, and the initial phase, are random variables with different distribution functions. Once the parameters are chosen, we obtain a time series which can be perfectly estimated for all times t after a measurement is taken. If we implement this random process in a simulation, take the amplitude at a specific time and plot a histogram, the result we get resembles the Gaussian distribution function. When we plot a histogram for other time instances, we get similar results. Hence, we can define probability distribution and density functions for random processes. These functions will generally depend on time. We have other statistics for random variables. Now let's see how these statistics can be utilized for analyzing the random process. Here we consider the first order statistics, which mean we consider the statistics of a single random variable. We can talk about the mean of a random process, which is again a function that depends on time. We will investigate the dependence on time later. For the moment, let's consider the double-faced coins example. To be able to calculate the mean, we have to replace the heads and tails with numbers. Let's substitute 1 for heads and 0 for tails. The probability of choosing the heads coin is equal to the probability of choosing the tails coin. Once the coin is selected, we know that throughout the time series, we will get only 0 or only 1. However, for calculating the mean of the random process, we are interested in the statistics of possible outcomes at any given time. Here, the randomness of the controlling parameter, selection probabilities for each coin manifests. At any given time, we expect to see heads represented by 1 in half of the experiments. We expect to see tails represented by 0 in the other half. This defines the probability mass function, which is used in the equation at the bottom of the slide to calculate the mean of the random process. Since each instance of the random process is a random variable, we have multiple random variables and we can use higher order statistics to investigate the relation between these multiple time instances. Consider the second order statistics, which deals with the joint distribution of two random variables. If we take two separate instances along the random process, we have two random variables and we can define the joint distribution of these two random variables. On this slide, you can see the definition of the second order distribution and density functions of a random process. But why are we interested in these second order statistics? We will see in the coming slides two very important second order statistics, the autocorrelation and the power spectral density. Essentially, we are interested in figuring out how the two time instances of a random process are related to each other. So let's define the autocorrelation of a random process. Autocorrelation relates the two random variables which are obtained by taking two time instances of a random process. It gives an indication of how the two instances of the random process change in relation to each other. Here, please note the time dependence. We will see more on this later. Having defined the first and second order statistics, we can now introduce a special class of random processes, namely the stationary random process. The formal definition is as follows. The statistics of a stationary random process do not change if the time origin is shifted by some epsilon. What does this mean? If we introduce a delay, we still observe the same first, second, and higher order statistics. This statement is formally expressed at the bottom half of the slide for the first and second order statistics. Now let's have a closer look at these formal definitions. The first order statistic derived from the probability density function is the mean of the process. By the definition of stationarity, we should get the same expected value for a time instance t and t plus epsilon, which means that the expected value is actually independent of time. So, the expected value for a stationary process is constant. When we consider the second order statistics, we should displace the joint density function by the same epsilon as the definition of stationarity concerned the displacement of the time origin. Now, both t1 and t2 are measured with respect to the same time origin. So, displacing that time origin amounts to displacing both t1 and t2 by the same epsilon. The second order statistic derived from the joint density function is the autocorrelation. What we consider at this point is the relation between t1 and t2. We can express t2 as t1 plus a time difference, tau, which reveals that the stationarity condition for the second order statistics amounts to the autocorrelation solely depending on the difference, tau, between time instances. This condition for stationarity can be extended to higher order density functions and statistics derived from those. If a random process is stationary for all such statistics, that random process is stationary in the strict sense. Let's consider the ways to relax this condition for strict stationarity. We can define stationarity of finite order, which means a random process is stationary up to a certain order n, but is not stationary for orders of statistics higher than n. A particular case is of importance here: processes that are stationary in second order. In other words, those processes that have constant mean and autocorrelation depending only on the time difference are of interest. We call these wide sense stationary. But why specifically the order 2? It has to do with the Gaussian processes, statistics of which are uniquely determined by its mean and autocorrelation. Gaussian processes have an important role in signal processing application. Before we finish, we should underline another important property. A wide sense Gaussian process is also stationary in the strict sense. For other processes, we can say a process is wide sense stationary if it is strict sense stationary. But we cannot say the reverse is true. A wide sense stationary random process does not have to be strict sense stationary. That is, unless it is Gaussian. The power spectral density of a random process is defined as the Fourier transform of its autocorrelation. Consider the random nature of the process. The Fourier transform of each realization will also be a random process. What we are interested in is the spectrum of the statistics. The Fourier transform and inverse Fourier transform presented in this slide operate on the autocorrelation and the power spectral density respectively. There are some important properties for a real random process. The autocorrelation is real and even. Remember that for a stationary signal, the autocorrelation depends solely on the time difference parameter. A change of sign of the time difference is the same as changing the order of the random variables in the joint expected value expression, which does not change the result. So the autocorrelation is real and even. The power spectral density is also real and even. To identify a random process, we need to determine its statistics. This may involve running many experiments to sample the distribution of the control parameters. Frequentist approach, as it is called, involves repeating the experiment many times and deriving the statistics from the observations collected during multiple experiments. However, we might not be able to conduct multiple experiments. Consider a sensor which gives noisy outputs. When measuring the environment, conducting multiple experiments means collecting multiple measurements for the sole purpose of estimating the noise statistics. Rather than doing that, we would prefer estimating the noise statistics from a single measurement, a single time series. But is it possible to do so? For an ergodic process, the answer is yes. The formal definition of ergodicity is as follows. The random process xt is ergodic in mean if time averages equal ensemble averages. Whether we repeat the experiment multiple times and calculate the mean or average the observation in a single time series, we get the same result. Note how we say ergodic in mean. A process can be ergodic for some statistics and non-ergodic for some others. Also note that the formal definition says the time average is equal to ensemble average in the limit. This is a very important point. When dealing with random processes, estimations based on a limited number of samples will also be random. If we estimate a parameter by evaluating a batch of 10 experiments and repeat the estimation with another batch of 10 experiments, our results will differ. Only with infinitely many experiments can we reduce the variance of the estimation to zero. Of course, this is if the estimator is consistent.